Hello students, welcome back in our video lecture series on design of steel and RCC structures. In today's lecture number 15, we will learn about design of bolted connection, or we will solve simple numerical on design of bolted connections. And this session will cover what are the points or principles which we have to observe in design and numerical on design of bolted connections. After completion of this session, we will able to design and will able to know a design of simple bolted connections. So first of all, let's recap previous session. So in previous session, we have discussed about shearing and bearing strength calculation and also solved a simple numerical on calculation of strength of bolt in bearing and shearing. So again, we will use these formulas in design of bolted connection. First of all, we have to know some of the points or principles which we have to observe in design of the connections. First, we have to know that, or we should design the strength of the bolted connections which should be more than the design load or actual load. And we should note that the center of gravity of bolts should coincide with the center of gravity of the connected members as we are designing simple bolted connections. So there should be no eccentricity between the CG of the bolts and the CG of the member. Again, we should know that the length of connection should be kept as small as possible. Okay. Also, we should know the IS specifications, and we should note that our connection will satisfy the requirements of IS 800 which are given in clause number 10.2. That is, pitch distance, we know the minimum pitch should not be less than 2.5 times D, or pitch provided in the connection should be more than 2.5 times the nominal dia of the bolt used. And the edge distance, we know the minimum edge distance should not be less than 1.5 or 1.7 times the diameter of the hole. Yes, 1.5, 1.7. Why these two values? Can anybody answer this? Yes, 1.5 times diameter of hole is for the machine or flame cut edges, and 1.7 is for hand flame cut or rough edges. Point number 5, we should know the diameter of holes for the different diameter of bolts. We know for 12 and 14 mm dia of the bolt, the dia of hole will be D plus 1 mm, that is 13 or 15 mm respectively. And for the diameter of holes, diameter of bolt 16 mm to 24 mm, the diameter of hole should be D plus 2, or that is 18, 22, 24 and 26 mm respectively. And for the diameter of bolts greater than 30 or 27, the diameter of hole will be D plus 3 mm. These should we know before designing the connections. Also, we should know the how to find plane area of the bolt shank, or area of the bolt at plane shank, that is pi by 4 into d square, and the calculation of the area of bolt at threads, or net area, that is 0.78 times pi by 4 into d square. Also, we should know about the material properties of bolts for different grades. For grade 4.6, we should know yield stress and tensile strength of the bolt. That is, for 4.6, yield stress is 240 MPa, and tensile strength is 400 MPa. And for 4.8, yield stress will be 320 MPa, and FUB, that is ultimate tensile strength, will be 420 MPa. Likewise for 5.6 grade bolt and 5.8 grade bolts. These values we should know before starting the design. As we have known about these points, let's solve a simple numerical on design of the bolted connections. Here there is a numerical. Design a lap joint to connect two plates of width 100 mm if the thickness of one plate is 12 mm and another is 10 mm. The joint has transfer working load of 100 kilonewton. In previous session we have just solved bearing and shearing strength. Now here we have to design. That means we have to provide number of bolts and along with its connection details, that is pitch and edge distances. For this we have to know how much load this connection is going to transfer. Here the connection has transfer a working load of 100 kilonewton and the plates are of grade 410 and we have to use bearing type of bolt, and also at the end of the design we have to draw connection details. So first of all let's assume diameter of bolt as M16 of 4.6 grade. We know nominal dia will be 16 and diameter of hole will be 18 and ultimate tensile strength will be 400 Newton per mm square. We can easily find nominal shear strength of bolt by using the formula as we have just discussed in previous session. So the nominal shear strength will become 36 kilo Newton and design shear strength will be equals to nominal strength divided by factor of safety, that is equals to 28.9 kilo Newton. After that we should know the terminology, there is pitch, edge and gauge distances, because we have to draw the connection details. Also we have to calculate bearing strength. So here as we know minimum pitch will be 2.5 times E. In our case it will become 40 mm and minimum edge will be 1.5 times D as we are assuming machine cut or machine flame cut edges. Hence minimum edge will be 27 mm. Let's round up these values. Provide pitch as 40 mm and edge as a 30 mm. Now strength calculation in bearing you have already calculated in previous session. We know how to calculate it. In our case KB will be 0.49 and thickness of thinner plate we know 10 mm and ultimate tensile strength of the bolt is 400 Newton per mm square for 4.6 grade bolt. So by using simple formula of nominal shear strength of bolt, nominal bearing strength of bolt, we can find the bearing strength as 78.5 kilo Newton, and by applying factor of safety we will get design shear strength of M16 or design bearing strength of M16 bolt as 28.974 Newton. Here design strength of bolt, how we have to find? We know the bolt value. Bolt value is nothing but the least of the bearing and shearing strength. Okay. So here least strength will be 28.974, that is in shearing. Hence design strength of bolt will be 28.97 kilonewton. Now as we know the design strength and also we know working load, the nominal load 100 kilonewton. By applying factor of safety we will get design load as 100 into 1.5, that is equals to 150 kilonewton. Now hence number of bolt required. How to obtain this? Yes, we have to calculate number of bolts required by simply dividing the load to be transferred or design load to be transferred by the connection by the strength of one bolt, that is 28.974 kilonewton. We will get number of bolts as 5.18. So by round upping it we will get or we will provide number of bolts as 6. Now by rearranging we can draw the connection details likewise. Here you can see there are two plates connected by means of bolt. Here number of bolts are 6. We arrange in 2 rows, 3 bolts in single row, 3 bolts in other row. All bolts are connected or bolted in chain bolting pattern. Here there is a 30 mm edge distance and these are the pitch distance, that is 40 mm. Again minimum gauge is nothing but equals to minimum pitch distance, and here provided as 40 mm. Also, we have to note that our width, as our width of the plate is 100 mm. Let's cross check it. As we are provided edge is 30 mm. 30 plus 30 60, plus this pitch is 40, means it will be equals to width of the plate, that is 100 mm. So likewise we can design a simple bolted connections. Hope you understand this. So today we will stop here. These are some of the questions. Now, although the design has been completed, but we have to again check this member for the plate strength. Bolts are strong as we have designed. What about plate? We have to check strength of plate in tensile. That is, we know TDN equals to 0.9 times AN into FU divided by gamma M1. Here, net area of plate is nothing but 100 minus 2 times D into thickness. That is, in our case, the critical section will carry the two number of bolts or two bolt holes which are in chain bolting. Hence, B minus and ds into T. This will be the formula for net area calculation. That is 100 minus 2 into 18 into T is 100. Multiply by Fu for plate is 410. Divided by gamma M1 will be 1.25. So by calculating on calci, we'll get design tensile strength as 188.92 kilonewton. Now, how can we say it is safe or not? Or plate is safe under the loading or not? Then for that we should note that the design tensile strength of plate should be greater than design load applied. In our case, design load applied is 150 kilonewton, hence it is safe. Now these are some of the questions for practice. You can note it down. Okay, thank you. We'll see you in next session.